So I hope that doesn't repeat today. So I had to actually move to another slower computer to generate the videos. So then I share my screen. So we see the doccam. Okay. So, and as I said, we are in section 4.8. And what we did yesterday, we took the matrix, which was 1, -3, 4, -2, 5, 4. So this matrix was already yesterday on the video, so you don't need to repeat to copy this again. 9, -1, 8, and 2. 2, -6, 9, -1, 9, and 7. -1, 3, -4, 2, -5, and -4. And because I don't like to write down these vector one more time, I say, okay, so these rows, 4 rows, each row vector has 6 components. I call R1 transposed, R2 transposed, R3 transposed, and R4 transposed. So R1 would be, for example, 1, -3, 4, and so on. And then we also have here 6 columns. Even it's not a good notation to call them C, because very often C stands for coefficient, but still, because C also can stand for column, I call them C. So I hope that's not too confusing. So we have 6 columns from this matrix. And so what we are looking now is, again, what we already introduced in the previous section. We're looking for the span of the row vectors. So span of R1, R2, R3, R4. So this is obviously a subspace of R6. And we can also look for the span of the column vectors. C1, C2, C3, C4, C5, C6. And that's obviously a subspace of R4, because every column has 3 components. All these vectors live in R4. Okay, so yesterday I wrote down, and then remember what I did, I actually extended this by a 0 column to just pretend I solve a homogeneous linear equation system, but that was really not the point. That was just to give some idea to introduce variables x1 to x6. So what we did is we used our Gauss-Jordan algorithm to generate the reduced row echelon form. And again, I write it down. Hopefully that's enough space. And we ended up with 1, -3, 0, -14, 0, -37. And there was a 0 column here, which I don't write. The 0 column would come from your right-hand side, but in the moment I skipped this. So then we had, next one was 0, 0, 1, 3, 0, 4, and 0, 0, 0, 0, 1, 5, and then 1 row was totally 0. So this is what we got after a few steps of the Gauss-Jordan algorithm, and we see that we have here 3 leading ones, and we have here 3 rows, and again, 3 rows which are non-zero. The 0 row doesn't contribute to the span, because the span of the 0 is just a 0 vector. And we have also 6 columns, but we see only these columns are enough. With the help of these columns, we can actually make every column vector. And remember also, I sometimes say all the leading ones are put in the front, and then we get here an identity matrix. Something I did yesterday. And so in order to do this, you have to switch the columns in the right way. So which means you renumber your variables. I might do this later, but first we do the following. So here, okay, so keep in mind this is the row space, and that's the column space. And now we can also have here a row space. And this time I write the vectors. It's the first row is 1, -3, 0, -14, 0, -37. Then we have 0, 0, 1, 0, 0, 1, 3, 0, 4. And then the final row we need is column number 3, 0, 0, 0, 0, 1, 5. And then we have also a column space here, which is given by the first column, the third column. So I just take the columns with the leading ones. No? And I don't need the other columns because this column is -3 times this column is -14 times this, plus 3 times this, and this column is -37 times this, 4 times this, and 5 times this. So I only need these 3 columns from the leading ones. And the 3 columns from the leading ones up here, together with the 0 here, 0 here, 0 here, 1 there, 0 there, 0 here, 0 there, 1 here. That also shows these 3 columns, these 3 rows, which are obviously non-zero, but because here we see our identity matrix again, distributed over several rows, these are also linear independent. That automatically comes out of the Gauss algorithm. So the rows which are left in the reduced row echelon form are automatically linear independent, and the columns of the leading 1 columns are automatically a spanning system for all the other ones. So we can forget about all the other columns. Okay, and as I said yesterday, the nice thing about the Gauss algorithm is now the row space from here and the row space from here are actually the same. So whatever you can make with these 3 rows, you can also make with these 4 rows. It turns out, because remember when we did the Gauss-Jordan, you don't see this in the moment. During the Gauss-Jordan, we didn't switch rows in this case. Sometimes you switch rows, but in this case, it's not. So what this means, these 3 rows came from these 3 rows. But it means the 4th row we actually don't need for the row space, because it turns out because the 0 row means essentially we could make this row with the help of the other 3 rows. So it turns out the row space here and the row space here are the same, and because we didn't interchange any rows, these 3 rows make the same span as these 3 rows. If I would have switched, I would have remembered where the rows actually went. When you look at the column space, you see all these columns have 0 in this last component, and they don't. So the column space obviously is not the same. But the good news is, and that's again not so difficult to see, so okay, the column space is not the same, but the dimension of the column space is the same. So here we have 3 linear independent vectors. So dimension is 3. Then the dimension here is also 3. So you have 6 vectors, but they only make a 3-dimensional space. That means you can pick 3 of them and they make the other 3s. Okay, and that's now really great. And also here, keep in mind here the row space, because it always depends on the number of leading ones. This dimension is also 3. So it turns out for the Gauss-Jordan matrix, it's the reduced row echelon matrix. The Gauss-Jordan is our algorithm. For the reduced row echelon matrix, it's obviously that the column space has always dimension equal to the number of leading ones, and the same thing with the row space, because the number of leading ones tells you how many non-zero rows there are, and because of the leading ones, this number is also a linear independent number of vectors. So for reduced row echelon, it's obviously because of the structure that the dimension of the column space of a matrix in reduced to echelon form is always equal to the dimension of the row space. Okay, so that we have here 3, 3 is not a surprise. That's always the case. But because they are equal here, that means because this was just an example, every matrix can be brought to reduced to echelon form. Then this and this is the same for every reduced to echelon form. That means for every matrix, the number of, also the dimension of the row space and the dimension of the column space are the same. Okay, so, and this is actually really, again, I would say that's the last insight into matrices, which kind of comes as a surprise. All the rest you see in this section is then just a little bit counting and thinking about what can happen if we do the Gauss algorithm. So I think the rest is actually not so surprising, but I remember when I was a student, it's very hard to understand. So you have 6 columns and 4 rows. If it turns out only 3 of these rows are linear independent, automatically from the columns, there are also only 3. That's kind of, why in the world would this be, no? It turns out if you're at the reduced to echelon form, that's clear, no? Because, yeah, how else? Because the ones tell you how many columns are linear independent, and then by the way, let's say three columns, then automatically there are also only 3 rows which are non-zero. So here it's kind of clear. But here it's, also, to me at least, that is kind of very surprising that if you make any matrix you like and you put in 4 independent rows, then you can have only 4 independent columns, no matter how big you make the columns. So, okay, but nevertheless, and the argument is very easy. It's the thing which we know since the first day of class. It's the Gauss-Jordan algorithm. But we understand now actually better what it does. Remember when I told you if you like to prove this, it's very important that from here to here, you multiply by elementary row operation matrices. The elementary row operation matrices are all invertible. And that's actually behind that this column space and this column space have the same dimension. It means if you have linear independent vectors, you multiply them by an invertible matrix, they stay linear independent. I mean, a lot of things actually we have learned are reasons that this is actually the case, but by now we have them all together. Even we skip the proof here. As I said, it would not be too complicated. Okay, so this I would say is the major thing. And a lot of things in this class, I would say you can forget after you finish the class. In some sense, it's not what you need, but something which if you are able to remember for later is that for every matrix, the row space and the column space have the same dimension. That's maybe something you can try to remember. And this dimension, which is the same for the row and the column space, is called the rank of a matrix. So if you say a matrix has rank 5, that means there are 5 linear independent row vectors and 5 independent column vectors. Even the matrix is much, much bigger. It doesn't matter. If the rank is 5, there are only 5. So in some sense, nowadays, when you think about, there are things coming up, let's say in the last 15 to 20 years, which is called data science. They look at big matrices. And very often, the term rank of these matrices, rank is kind of a measure of information. So if a matrix, no matter how big there is, and nowadays they have really big matrices, that's why they need these big computers at Google and so on. The rank essentially tells you how much information is there. You can have 1,000,000 times 1,000,000 matrix and the rank is only 10,000. That means 10,000 out of 1,000,000 is a very small percentage. That means there are essentially only 10,000 informations in there. All the rest is just smoke and mirror. No? You only have to figure it out from the matrix. Nobody tells you which 10,000. No? So that's maybe another thing. It will not happen in our class. We are just doing the basics here. But the rank of a matrix, if you think about from a statistical, also in statistics you have matrices since hundreds of years. Nowadays they call it data science. The rank of a matrix is somewhere related to how much information is in the matrix. Yeah. Because independence means always information in some way, but once you have information in your rows. No? Okay, that's also, now I continue here. So theorem 4.81, the row and column space of every matrix has the same dimension. Okay, so this is an important result. So if you have 3 independent column vectors, you can also have only 3 independent row vectors and the other way around. And now this dimension, as I said, gets a rank, gets a name, and we call it the rank of a matrix. But before I say this, I repeat one more time this picture from here to here in the general case. And this time I sort my ones at the beginning, so we have a clear understanding of all the numbers flying around here. So it's actually only 3 numbers, no? How many columns you have, how many rows you have, and what's your rank, no? Okay, but before I define rank, I do one more time the picture so we have this in front of us when I write down the next definition.